Hi everybody, this is Mr. G here to talk to you about exponential functions. This is the first of several videos. We're going to start section 10-1. This is part 1. Put the second part up here tomorrow. Let's start off with what is an exponential function. Well, what is it? Well, the basic form of an exponential function is y equals a times b to the x. Alright? Well, what does that mean? Well, a, b, and x here are here. Let's talk about each one. X is what x has always been. It's the x-axis, and y is the y-axis. And the x-axis in exponential functions most of the time is time. A is the initial amount, and an initial amount, like in linear equations, is the y-intercept. It's where the graph crosses the y-axis. And then finally the last one, and the most important, is the base, which is also called the rate. And this is what is critical about exponential functions, is that rate. Well, let's just jump right in and graph one so you can see what's going to happen here. Let's graph the function y equals 2 to the x. Now I'm going to leave out the a for the moment, and let's just call a equal 1. Just for the moment, we're going to let it be 1, and we're not going to keep writing it, so I just didn't want to worry about it. Okay? Let's make a table of values here, and we're going to have our x, y values. We're going to start in the middle here, 0, 1, 2, 3, and let's go ahead and put these values in for x and see what happens. All right, 2 to the 0 is 1. Anything to the 0 is 1. And that's significant because that always happens. When you raise something to the 0, you get a 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Okay, so let's see what the graph is starting to look like here. Okay. Here's our x-axis. Also, we could call that t for time if we wanted to. And time 0 is now, and to the right here, as we go to the right, that's going into the future, and as you go to the left, you're going into the past. So now is the y-axis here. So if x is 0, y is 1. If x is 1, y is 2. If x is 2, y is 4. And if x is 3, y is 8. 4, 5, 6, 7, 8. Y is 8. And what we're getting here is not a line, but it appears to be a curve. Okay? And that curve is growing increasingly, and it's not a steady rate. It's not going up at the same amount all the way along here. It appears to be increasingly steeper. Well, what happens if we go back in time? Let's put -1 and -2 and -3 in here. 2 to the -1. Well, what happens if we take something to the negative power? Well, we have to put that on the bottom of the fraction now to the 1, and this is actually a half. How about 2 to the -2? Well, that would be 1 over 2 to the positive 2, or 1/4. And 2 to the -3 is 1 over 2 to the 3 is 1/8. Well, let's graph that. -1 goes to a half. -2 goes to a quarter. -3 goes to 1/8. Looks like we're getting closer and closer to the x-axis, and that continues to get closer to the x-axis. And it gets so close, but it never actually gets there. The x-axis in this situation, and we'll talk about this later, the x-axis in this situation is what's called an asymptote. An asymptote is a line where a graph approaches it but never actually gets there. But we'll talk about asymptotes later. But the main thing for right now is to note that's what's happening to these numbers. Every time we move 1 unit to the right, go 1 unit bigger, what's happening? The numbers are doubling. Times 2, times 2, times 2. In fact, all the way back into negative. Eighth times 2 is a quarter times 2 is a half times 2 is 1. The numbers are continually doubling. Well, that's the rate. 2 is that rate, and it says it's doubling. If I had a 3 here, every time we moved on the graph, it would be tripling each time I moved to the right. 2 is the rate, and that rate is a multiplier. You'd multiply by 2 and multiply by 2 each time. Now, if I went back in time, it's like dividing. So if let's say that 0 is today. Yesterday would have been a half. The day before that was a quarter. Tomorrow would be 2, and the day after that would be 4, and so forth. As we go, through on time here, if now is 0, then we can go back and forth and figure out what the value would be at any place in time. Now, it'd probably be a good idea right now to take a minute to talk about how linear equations, which we've been using for a long time, compare to exponential equations, just so we have an understanding here. Okay, the y-intercept form for a linear equation is y equals mx plus b, and exponential, we said, is a b to the x. Now notice that the b here and the b here have nothing to do with each other. Don't get them confused. Let's see. B over here stands for the y-intercept, also known as the initial amount. So if we were to graph this, let's say we have an equation y equals 3x plus 1. The initial amount is 1. Okay, and m is that thing called the slope, also known as the rate. So there's a rate in here too, but the rate's different. Let's say that the slope here is 3. That's a rise of 3 and a run of 1, so up 3 and over 1. Well, it goes up 3 again and over another 1. Notice that we could do this forever. It always goes up 3 and over 1. This is a straight line. Well, that's why it's called a linear equation, right? So the slope here is actually done by adding the same amount every time. I'm adding 3. Every time I move to the right, I move up 3. It adds the same amount. Well, as we just saw with exponential equations, every time you move to the right, let's go back to y, let's do y equals 3 to the x, okay? So we can make a table here. If x is 0, y is 1. If x is 1, y is 3. If x is 2, y is 9. If x is 3, y is 27. So let's graph that. 1, 2, 3. And 2 goes up to 9. 4, 5, 6, 7, 8, 9. And then 3 to the 3, well, that's way off the graph here. But what's happening, and the same thing would occur back here in the negative region, is every time I move 1 unit to the right, I'm multiplying by 3. Every time we go here, we multiply by 3, multiply by 3, multiply by 3. So linear equations are adding the same amount every time, and exponential equations are multiplying by the same amount. Linear equations, we call them arithmetic sequences, and exponential equations, we tend to call them geometric sequences. All right, something that probably needs to be mentioned here is that when we talk about the rate in a linear equation, we usually use the phrase something per something else, like dollars per hour or feet per second. Okay? But in exponential equations, when we talk about the rate, we usually use the phrase by a factor of. By a factor of. Because, well, what's a factor? Well, factors are multipliers. And so if you're going by a factor of 2, every time you're multiplying by 2. It's not some consistent amount per hour or per day or whatever. All right, now we need to spend a little time talking about the rate, because these are kind of critical questions. The rate can't be anything. There are some restrictions. There are some restrictions on what the rate can be and can't be. For example, let's take a look at y equals 1 to the x, y equals 0 to the x, and y equals, say, negative 2 to the x. All right, there are restrictions on the rate, so let's make a table here and see what happens. If the base is 1, what goes on here? Well, 1 to the 0, anything to the 0 is 1. 1 to the 1 is 1. 1 squared is 1. 1 cubed is still 1. Notice what's happening. The base is causing this line to actually be a flat line. It's a horizontal line. There's no exponential growth here. So this is not possible to have a base of 1. Something similar happens when the base is 0. 0 to the 0, well, I'm not sure what that means exactly, but 0 to the 1 is 0. 0 to the 2 is like saying 0 times 0, well, that's 0. 0 to the 3 is 0 times 0 times 0, and that's also 0. So once again, we've got a flat line at 0. This is not growing either. It doesn't make any sense. And probably the most interesting of all is if the base happens to be negative. Let's see what happens here. If x is 0, negative 2 to the 0, well, that's always 1. Negative 2 to the 1, negative 2 to the 1 is a negative 2. Negative 2 squared, well, that would be a positive 4. Negative 2 cubed, well, that makes this a negative. The sign's flipping back and forth here, would be a negative 8. And negative 2 to the 4th, now we're back at positive 16. Well, this is really odd. What happens if we tried to graph this is we'd end up with, well, let's see, 0 goes to 1, and 1 goes to negative 2. Now I'm going down. 2 goes to positive 4. Now I'm going back up here. 2 goes to positive 4. 3 goes to negative 8. Now we're back down here at the bottom, so I'm running off. And and the next one's way up here. So what's happening? Well, this graph is vacillating back and forth between positive and negative, and it will continue to do so. It continues to do so forever, back to infinity. In fact, if I used a bunch of fractions here, this thing would be vacillating back constantly an infinite number of times. It look like this. In fact, it's totally weird. So it tells us that the base cannot be negative either. So in conclusion, we find out that the base cannot be equal to 1, and the base cannot be equal to 0, and the base cannot be negative. So how do we summarize this? Well, we would say that the base is greater than 0, but it cannot be equal to 1. Put a box around that and hang on to that, because that's the restrictions on the base. The base has those restrictions. All right, there's one other very important thing about the base we need to talk about. We haven't talked about what if the base is a common fraction. So we have y equals b to the x. What if we made this a common fraction, like a half? We're going to raise the top and the bottom to the x power. So here we go. If x is 0, 1, 2, and 3, and let's go back in the negative as well, see what happens. All right, 1/2 to the 0 power. Well, anything to the 0 power is always 1. 1/2 to the 1 power is a half. 1/2 to the 2 power. Well, 1/2 squared, I'd square the top and get 1. Square the bottom and get 4. It's 1/4. 1/2 to the 3rd power. Well, I'd cube the top and I'd get 1. I'd cube the bottom and I'd get 8. Now, what's happening? You can see the fractions are actually getting smaller. What happens if we put a negative exponent in here? 1/2 to the negative 1. Well, that makes this flip over and become 2 over 1 to the 1, or 2. And the 1, negative 2, I don't have the room here, but if I go back this way to negative 2, 1/2 to the negative 2 is 4. So what's that graph look like? Well, 0 goes to 1, 1 goes to 1/2, 2 goes to 1/4. Now it's getting smaller. 3 goes to 1/8. Let's go back this way to negative. Negative 1 goes to 2. Negative 2 goes to 4. Oh. We got the same numbers, but now they're going the other way. They're going downhill. And what we find here is that when the base is a fraction between 0 and 1, now remember, it can't be 0 and it can't be 1, so they're not equal. When the base is between 0 and 1, we call this decay. The word decay simply means it's decreasing. It's going down, decaying. Something's kind of falling apart. It's decaying, okay? Whereas the graphs we looked at before, if the base was greater than 1, we called this growth. Well, these are two very important points that need to be made, and this is part of your assignment today, is when the base is greater than 1, it's growth, and when it's between 0 and 1, it's decay. So if you wanted to summarize the base again, we could say the base is greater than 1 is growth, and the base sandwiched between 0 and 1 is decay. Notice the base cannot be 0, it can't be 1. If it's above 1, it's growth, and if it's between 0 and 1, it's decay. This is important because the fractions that you get in a problem will tell you whether it's going to be growth or decay. So let's take a look at some numbers, and you're going to have these to do on your homework. If growth, the base is greater than 1, and decay, the base is between 0 and 1. That means if you have the equation y equals b to the x, if b is, let's say 2, that's growth. 7.3, 1.1, as long as it's bigger than 1, and 8. Those would be growth. This is growth. Here, if the base is a common fraction, like 1/2, or 1/3, or a decimal, like 0.7. But notice 8/5 is not a common fraction, because in reality, this is 1 4/5, so it doesn't belong here, it belongs over here. It's not a common fraction. So decay is those numbers, and the graph will go downhill. Graph will go down for these, and over here the graph will go up. All right, let's take a minute to talk about the initial amount, A. We've been leaving this out all along, but really it's been 1. It's been there the whole time, we just haven't been using it. What if we had an equation like y equals 3 times 2 to the x? Well, let's make a table of this, okay? And same thing will apply here. Let's go negative 1, 0, 1, 2, and 3. If x is 0, well, 2 to the 0. Notice I'm doing the exponent first because you can't multiply until after you've done exponents, order of operation. So don't go 3 times 2. 2 to the 0 is 1, times 3 is 3. Well, that makes perfect sense because 0, 3 is right on the y-axis. That's my initial amount. That's today. So the initial amount is that number right there. Doesn't even matter what the base is, because if that's a 0, that is the initial amount. 2 to the 1 is 2. 2 to the 1 is 2, times 3 is 6. 2 to the 2 is 4, 4 times 3 is 12. 2 to the 3 is 8 times 3 is 24. And notice it's multiplying still by 2. The rate is changing by 2. 2 to the negative 1, well, that's 1/2 times 3, or 3/2. So we get the same idea here. 1 goes to 6. 2 goes to 12. 7, 8, 9, 10, 11, 12. And negative 1 goes to 3/2. That's 1.5. We get the same thing here. But the key here is that the initial amount is that number A. And that's going to play a crucial role in tomorrow's assignment. So hang on to that thing. Okay, there's one last thing about growth and decay. Sometimes you're going to see a problem where the exponent is negative. Look right here, the exponent's negative. So you might see something like this, y equals 2 to the x over here. You might get a problem, y equals 2 to the negative x. Well, initially, when you're in a hurry, it looks like the base here is greater than 1, so it looks like this is growth. But let's see what's really going on here. If you were to graph this, let's go ahead and graph it. If x is -1, well, what's a -1? Well, that's 2. Or you could look at it this way. What do you do to change this? Well, let's go ahead and go 1 over 2 to the x power. Oh, that's another way of writing the same thing. Well, now you can see that the base is really a fraction. So this is actually decay, even though initially it looks like it's growth. It's decay. So watch what happens if we plug this in. If x is 0, 1/2 to the 0 is 1, 1/2 to the 1 is 1/2, 1/2 to the 2 is 1/4. So see, it's going downhill again. So this is in fact decay. If you had a problem like this where it was 0.2 to the negative x, well, it appears initially that looks like it's a decay problem. But because it's got a negative exponent, well, this is 1/5. I raise 1/5 to the negative x power. Well, the negative tells me to flip the fraction over and put to the x. So this is y equals 5 to the x. Oh, it's really growth. This is a growth problem. So be on the lookout for that negative exponent up there, because that might confuse you, because you might think that's growth, but in fact with a negative exponent, that. All right, the last thing we need to talk about today is solving exponential. Well, before we do that, we need to kind of review some of the principles of exponents. Solving exponential equations, we have to use the same rules that we've been using all along. So let's review those. Here they are. X to the third times x to the fourth. Well, when the request is to multiply two things with the same base, you add the exponents. This would be x to the 7. X to the third raised to the fourth power. Well, when you're asked to raise something to a power, you multiply the exponents. So this is x to the 12. And x to the, say, 7 over x to the third, when you're requesting division with the same base, you subtract the exponents. 7 minus 3 is 4. Those are the rules we've been using all along. All right. Now we're going to solve exponential functions here, but later in the course we'll be solving them more with logarithms, which is the method for using them when they don't have the same base. But we're going to use a little technique that I'm going to call smell a base. Smell a base. And you're going to get problems where you're going to have to be able to look at a number and go, oh, I recognize that number. It has that particular base. So for example, 2's, all the powers of 2, you should know 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, and so forth. You should recognize all of these numbers, when you see them, go, oh, that's 2 to something. That's 2 to the first, 2 to the second, so forth. 3's, 3 to the first, 3 to the second, 3 is 27, 3 to the fourth is 81, 3 to the fifth is 243. That's probably high enough. 4's, 4 to the first is 4, 4 to the second is 16, 4 to the third is 64, 4 to the fourth is, 256, 4, and then 5's, 5 to the first is 5, 5 squared is 25, 5 to the third is 125, 5 to the 4th is 625. These are the main ones that you're going to need, but you've got to be able to recognize, oh, 81. That's 3 to the 4th power. You've got to be able to recognize them to do this assignment. All right, our first problem today is going to be 3 taken to 2 to the n plus 1. Notice I'm writing that exponent plenty small and high. Now, as I look at this first problem here, let me cover up this other mess here so you don't have to look at that. As you look at this first problem, do you smell a base that's in common between these two? 3, and this has got a 3 for a base. What is that? Oh, that's 3 to the 4th power. 3 to the 4th power. Now, it stands to reason that if the bases are the same, won't these exponents have to be equal as well? Well, that makes perfect sense. They both have the same base. The exponents would have to be equal. So then we're going to jump out and into the down here, bring this exponent down into the real world here and solve it. And we just solve the way we usually do. Oh, I'm out of room here, so let's go back up here. Subtracting 1, I get 2n equals 3, or dividing by 2, n equals 3 halves. So we find that the exponent here would have to be 3 halves. Okay? All right, let's do this one. Well, look at these bases. Do you smell a base here? Somebody says, oh yeah, 8, isn't that 4 to the... No, that's not 4 to anything. But they both have the same base of 2. So 4 is 2 squared, and I'm going to write 4 as 2 squared and then put the base on top of the parentheses here. And 8 is what? Oh, that's 2 to the 3rd. And I'm going to put its exponent up here. So this is exactly the same as what we had before. I smelled that the bases were both 2. Now, this isn't exactly good enough yet to solve them like we did the last one. What we have to do is look at this as powers of powers. Oh, I multiply the exponents here. 2 times 2x would be 2 to the 4x, and I can get rid of the parentheses. What's this? Oh, this is 2 to the, well, I multiply here. I'm going to have to distribute too, aren't I? 3x minus 3. Oh, now I can get rid of the parentheses, and this is 2 to the 3x minus 3. I distributed that 3 in there. Now, if the bases are the same, we can, in fact, set the exponents equal to each other and solve it like we did before. Subtracting 3x, we get x equals a negative 3. So there you go. X is a negative 3. And you can solve these using this thing I call smell a base. Later on in the course, we'll be solving them with other methods, but you need to be able to know a base when you see it and go, oh, I recognize that one. All right, so we are at that point where you're probably ready to go ahead and do assignment A. It's only 16 problems here. You can skip 11 and 12, page 527, 1 through 18 all, and skip 11 and 12. Now tomorrow I will give you the next little bit of this, which involves writing an equation. So go ahead and do the homework here, and I'll see you at the next video.